Alright, here's our first shear and bending moment problem. We'll do this problem in two ways. First, we'll use the indefinite integral method, the one that always works. It's a little bit slower, but you end up with all the equations for everything. And then we'll use the area under the curve, the definite integral method, which is faster, but it could run into problems for complicated loading scenarios. First things first, we have to determine the support reactions. This is a fixed support, so we'll have some fixed support couple moment and some force. There won't be a left or right force because there are no other left or right forces on our beam. So I can sum the moments about this point to figure out that fixed support couple moment. First, we'll have the single force that represents that triangular distributed load. And the magnitude of that force will be 1/2 the base times the height. So that'll be 250 newtons. And I'm going to measure the distance from that smaller end, because that's where I'm taking the moment about, which makes it 2/3 of my total length. That's just going to be 2/3 meters. And this moment will be positive. I've chosen my positive rotational direction to be counterclockwise. The rest of the moments aren't too bad. Got a 300 here. We have this 150 and a moment arm of that 1.5. Wanting to spin clockwise, so negative moment. And we have a 30 couple moment over here. Another positive. And finally, the fixed support couple moment itself, which I've assumed to be spinning us clockwise, so negative. So we can do the math on that. And I'll get this positive result. And positive means that my clockwise assumption was correct. So now I can sum the forces in the y. I have my fixed support force going up. I have my triangular distributed load going up, and this 150 going down. So I can solve for that F. And I got a negative 100, which means that force is actually going downwards. Alright, now I can start my shear process. I'll find all the shear, and then I'll find the moment diagram. So I need to determine the very first point on my shear diagram. So I'm going to look at the very first cut at x equal to 0. So what's happening on this cut? Well, there's 100 from the wall, and I got this 271. My positive shear is going to be this way, wanting to make the section spin clockwise. So for us to have balance here, my internal shear force really should be going up. That is, it should be going in the direction of negative shear. And its value, of course, must be equal to 100, so I can balance out that 100, so we can have force balance in the y. So my initial point is going to be a negative 100. And each one of my marks here will be of length 50. So there's negative 100. Alright, so now I can apply my process. I'm going to do the indefinite integral of my distributed loading. Well, that equation is going to be a 500 over 1 times x. Realize what I'm doing here is I'm making a line equation. A y is equal to mx plus b. Remember, the m is the rise over the run. My w forces, in a sense, are positive. So this is a positive 500 rise, and the run is 1. So my equation really is just 500x. And I always recommend testing these equations just to make sure they work. If I plug in 0 into x, I get a 0. Great, because I'm at 0w here at x equal to 0. Plug in a 1 into this equation, what do I get? A 500. Excellent. So it looks like this equation holds. So I have to take the indefinite integral of it to get my v. Not too hard of an indefinite integral. To find that c, I use my initial condition. I know that at x is equal to 0, my v is that negative 100. So x0 in here, negative 100 in for here. And this means that my c is going to be negative 100. So this v equation is valid as long as the w that produced it is valid. So it's valid until x is equal to 1. So just to establish the endpoint here, I'm going to plug in 1 into x, see what comes out for my v. You'll get a 150. So I know at x is equal to 1, I'll have this 150 here. And I know the line connecting them is going to be a parabola. We've got to be careful. A parabola could be like this or like this. Who's to say we can't draw it like that? It's still a parabola. Well, remember, we have a concave up parabola here. If the number, the coefficient to my square term is a positive, my parabola is concave up, and vice versa if this number is negative. So I know that this is what it looks like. We have an instantaneous couple moment here, but we know that that only affects the moment diagram, so we can ignore it. I keep moving a little bit forward, and I figure out that I don't have any w there. My w is 0. So I take the antiderivative of 0 to get my shear, and the antiderivative of a 0 is just a constant. And you can always check. You take the derivative of just a number, you'll get 0. So what constant will this be? Well, again, we can determine it. At x is equal to 1, we know our shear to be that positive 150. So that's what this constant will be. So from x equal to 1 to x equal to 1.5, we just have a constant 150. Now here is a point force. So I got to run through my process for that. If I have a point force of 150 coming in on that beam, I can't have my positive shear to fight against that. I know negative shear must be fighting to hold that up. So this 150 is going to result in a downwards drop of our V diagram by how much? 150. So that drops us down to the x-axis at 0 shear. And from then on, I have no distributed loading. My W is 0, and I know that that results in my shear just being a constant. And if you were to do that math, you just find it's a constant of 0. Doing the same exact steps we did over here. So there's my shear. The only tough equation for it is that initial parabola there, so I'll just save that. So now for the moment, I need some sort of initial point. So I'll think about that very first cut at x is equal to 0. I'll have the 271.7. And that downwards 100 Here's my positive internal bending moment direction, wanting to curl the beam up, make it smile. So to battle out this clockwise 217, I'll need a counterclockwise 217, or 271, sorry. So that puts our starting point way up there, 271.7. And now we can run our indefinite integral process. And here is my first shear equation to anti-derive. So doing that inverse power rule, I'll get an 83.3 repeating x cubed, a minus 100x, and of course a plus c. So that will be my moment equation. Got to figure out what that c is. We know at x equal to 0, my m is that 271.7. So I plug in 0 in for my x's, that 271 in for my m. Those zeros will destroy these guys, which means c basically has to be that 271.7. So if you're using this indefinite integral method, this is the one that you really want to have your graphing calculator on you for. All you got to do is just put into your graphing calculator. And this moment equation is going to be valid from the beginning to x equal to 1, just like this shear equation is. So I want to figure out the endpoint here to put that on my graph, which is really easy. If you have that equation graphed, you can just hit trace. We'll find out that m is approximately 255. That'll get us right here. And just looking at my graphing calculator, we have something like that. Now, I actually forgot to say this. Ideally, you'll want to figure out what these points of interest are. We have a shear is equal to 0 point here. And actually we have a local minimum for the bending moment here. And again, that's super easy if you have this equation graphed out. I can just hit second calc, go over to minimum, and I'll find that this minimum occurs at an x around 0.63, and that exact minimum there is a 229.5. And you can do the exact same thing for this, and you would find out that this 0 for the v occurs at that same 0.63 as well. That's no coincidence. The antiderivative of v is m, so consequently the derivative of m is v. So this graph is the derivative of my m graph. So if I know we have a local minimum here at this x, I know that my derivative must equal 0 at that same x. So, alright, moving on. That right endpoint of our m equation is 255. The next v equation we need to integrate is that constant 150 up there. Oh, but before I do that, I almost forgot that here's this 300 here. That's going to cause a down or up shift on our M diagram. Alright, so let me draw this out. Here's this external 300. Here is my positive internal bending moment. Now I'll need bending moment in the negative direction to fight against that external 300. So this is going to cause our diagram to shoot down by 300. So if I do 255 minus 300, that'll get us a negative 45. Alright, so just make sure you're watching out for those point applied loads. So now we can do the antiderivative of our next v equation. So we'll do the antiderivative of that constant, positive 150. And that will get us a 150x plus c. And we can figure out this c because we know our initial conditions. At x equal to 1, we have this m is equal to negative 45. So plug in 1 here, negative 45 in here, and we'll find that our c is equal to a negative 195. This m equation is valid until x is equal to 1.5. So here's 2. So we want to figure out what our m is at that x is 1.5. That'll just be a 30. So I'll be around here. And this is a line equation. Pretty easy to figure out this intersection point with the graphing calculator. Second calc 0. Go to the left bound, right bound, and we get that our m is actually 0 at x is 1.3. And it's 30 right here. Alright, our next v is this, and this is that another one of those integral of 0 situations. And we know that this results in our m just equaling some constant. Our m doesn't change from that 30. So this is going to be a constant 30 all the way up until our very last cut of x equal to 3. We'll want to perform our check here. Here's my last cut at x equal to 3. We have an external 30. Here's my positive bending moment. Nope, not going to work. We're going to need bending moment in the negative direction, which means this is going to drop us down by 30 until we hit 0. So equation, antiderivative, find the c, graph. Equation, antiderivative, find the c, graph. This indefinite method is pretty straightforward, and it really easily allows us to figure out all of these points of interest. Local maxes, local mins, and 0 crossing points. So we'll do the same problem but with the definite integral approach. We'll just be concerned with calculating the areas underneath all of these curves, which will get us the change in the v and the change in the m, rather than the entire equations. Alright, so here's our initial v and m values. Now if I want to sketch my w curve, that's going to be like this. Remember, these are positive w's here, because these w's are going in the positive y direction. So the area under this curve is just the area of a triangle. So 1/2 times the height times our base, which will get us a change in our shear of 250, positive 250. So if I go positive 250 up from this negative 100, that puts us at a positive 150. Now, because this w here is a line like this, we know that our v equation is going to be some sort of parabola. And it's going to be an upwards, concave upwards parabola, because my slope for my w is a positive, which will produce a positive coefficient here. So from that, I know the line connecting these guys is going to be like that. Let me draw that a little better. Yeah. Alright, but we still want to determine where this crossing point is. And this is where it gets a little fun. And this is why this second area under the curve definite integral method is a little more murky. Because if we had done it the first method, we would have just had the equation to this and used our graphing calculator, or at least plugged in 0 in for the v of that equation and found x that way. Well, here's our question. We want to be here. That is to say, we want our delta v to equal a positive 100. Well, how much area do we have to go under this W curve so that we create a delta V of positive 100? Well, our triangle formula is 1/2 times the base, which is going to be some unknown x here. It's going to be this. It's actually what we want to know. Now the height here, well, we don't really know that either. But because this is a line here, we know that we can write y, or even better, w. W is equal to the rise, which is from 0 here to 500 here, over the run from 0 here to a 1 here, times x. So w is equal to 500x. That is the equation that allows us to plug in an x, something like this, and produce the w at that x. So this is how we get the height. So we want this area under our triangle to produce a positive 100. All we got to do is solve for x. In doing that, we get a positive 0.63. And that's good because I'm pretty sure that's what we got last time. Alright, moving on. Our external bending moment does not affect it. There is a w of 0 on that bound. Just looks like that. No area underneath that curve, so we know that the change in shear will equal a 0 in between x is 1 and x as 1.5. So we know we're at a constant 150 until we get to that x of 1.5, because there we have that 150. We know from that argument that here's our negative 150. I'm going to need shear, negative shear, to balance it. So this brings us down by 150. And from then on, there is no w, which means no change from our current shear value. Alright, so now we got to find our bending moment diagram, which means we have to take the area underneath this parabolic curve here. The problem is that that's not an easy area to calculate. It's not like it's a triangle or a rectangle. So this is where this second method, the definite integral area under the curve method, really falls short in my opinion. And you would want to defer back to the indefinite integral method to figure this out. For at least our moment equation from x is 0 to x is 1, where we have this parabola going on. Once you're done with that, you can keep applying the definite integral method as long as you have some nice rectangles and triangles. But for now, we'll want to go back and do the indefinite integral method real quick. Remember, my W is a 500x. So if I integrate that to get my V, it's a 250 x squared plus c. We can figure out that c because we know that at x is equal to 0, the V is a negative 100, this guy. And that means the shear equation is going to be this. And now we can integrate again to get our moment equation. And of course, because we know at x is equal to 0, we have an m of positive 271.7. That means we know our c to be that same 271.7. So you can pretty quickly grab this using the indefinite integral method, especially if you're well practiced. So, bit of a wrinkle here, but we should be on track. We'll want to plug in our right bound. We know that this is going to be some equation that stops right here. Because remember, the V that produces it stops right here as well. So I want to know at x is equal to 1, what is the m? Well, again, just a calculation there. Just plug in 1. And we'll get a positive 255. So that'll be right here. So we got that. But still, how do we know what this curve is linking these 2 points without a graphing calculator? Well, again, here's where the Calc 1 comes in. This equation here, concave up parabola looking thing, one antiderivative gets us a cubic. Remember, a cubic is going to look something like this. So, which section of this cubic is the one linking my 2 yellow points? Well, check out my derivative here. Remember, V is the derivative of my m. Looks like my derivative values are negative, so we're going to be decreasing. Well, here's our m decreasing here. I hit a derivative equals to 0. Oh, here's a derivative equals to 0. And then my derivative is positive, which means my function is increasing. So here's my function increasing. So I think it's going to be something like this. We're going to have a local minimum right at that same x is equal to 0.63. And here's our positive function increasing, that positive derivatives, and here is our function decreasing. So we have our negative derivatives, we have our derivative equal to 0, that's your local min, and then my positive derivatives over here. So you can craft the shape by just knowing what information derivatives tell you. The derivative is that rate of change of your original function. And here we have a 255. Now to figure out what exactly the m is at that local minimum, well, we just got to plug in a 0.63 into that m equation that we now have. So again, just another plug-in at x is equal to 0.63. The m that we get will be a 229.5. So we'll want to put that in there. So I got that. So before I take the area underneath this V curve right here, I can't forget that here is this point applied couple moment. So real quick, I got to sketch that out. If here's my 300, and here's my positive m. Nope, that won't help me fight against that 300. Negative m will. So I know that this is going to cause us to drop by 300. So 255 minus 300 will be a negative 45. So right about here is where we'll end up. Alright. So looking forward, no more instantaneous couple moments until the end. So I can just figure out the area under this V. And that will be my change in m. So the area of that rectangle is going to be the base, which is a half. That's from x is 1 to x is 1.5, times the height, which is a 150. That area will be 75, and it's positive area, so it's going to be a plus 75. So by the time I get to an x of 1.5, my m will be 75 higher than this 45. And that gets us 30 right here. Now, we need to figure out what is the curve in between. Well, that equation there is just a constant 150. If I anti-derive that, we're going to get some sort of y is equal to mx plus b looking thing. And since this 150 is positive, my slope's going to be positive. This is just going to be a line, a straight line connecting these two things. And from there, my v is 0, so there is no area underneath this curve, which means my change in my moment for that will equal 0. So my moment is not going to change. So I'm at the very end. Got to do that very last check. Looks like we have an instantaneous 30 couple moment. I will need negative moment to fight that. So my moment diagram will shift downwards by 30 and get us to 0. So it gets really tricky when your W is a triangle like this, because that'll result in a quadratic, a parabola for your V, which will be impossible to find the area under just by, simple shapes. So you want to go back to our indefinite integral method for navigating these sorts of things. Oh, and really quick before I forget, let's just walk through how to determine where our m becomes 0. From 45, I know I have to go up 45 to get me 0. So how much area underneath this curve here do I need to go so I get a plus 45? Well, for this rectangular area here, my height is 150. What's my length, though? Such that we get a total rectangular area of 45. Well, I can solve that real quick. And that'll be a 0.3. So we need to go 0.3 out from 1 to get there. So at x is equal to 1.3, my m is 0. Ideally, you want to know all of those points of interest, local maxes, local mins, and those 0 points as well. Again, this area under the curve definite integral method is faster, but sometimes you will have to fall back on that indefinite integral method. So in my books, it's just better to do it the faster way, the definite way, when you can. But when you run into one of these situations, you know the indefinite integral, so you can do that fluidly as well. Alright, I hope this problem made sense. If you have any questions, feel free to post them in the comments.